Thompson, and I'm the Associate Director for Academic Programs at the UBC Institute for Advanced Systems Engineering, and I'm new. I started in August. Today our speaker is THEODORA'S Saunders from Sikorsky, which is now, of course, Lockheed Martin, and she may explain that a little bit, the merger. THEODORA Saunders, she has 2 master's degrees in electrical engineering and industrial engineering. Her expertise and her background has been in avionics and controls, and you might explain a little bit more in depth. She worked to develop the systems engineering process at Sikorsky, and she was in that for several years, probably 8 or 9 or 10 years, a long time. And in the last couple of years, she's transferred into a systems engineering program, and she's a chief system engineer responsible for the development of a combat rescue helicopter now at Sikorsky. She's, in my opinion, she's a person who really understands the research and the engineering design problem of systems, but also really understands how you develop a process and implement it in a wide scale, a big scale at an engineering company. And so I think there's a lot that you're going to be able to learn from her today about how they implement and actually do systems engineering at Sikorsky. So a couple of things I'm supposed to remind you is that there's 2 emergency exits in the back. There's bathrooms, one is on the left, one's on the right. And please turn off your cell phones. And I feel a little bit like a flight attendant right now, so please turn your cell phones off. And THEODORA, thank you so much for being here today, and we're looking forward to your talk.
Thank you. Hello, everyone, and thank you for the invitation. I have a slight accent. I came to this country, I was 22. I cannot lose the accent. It's a waste of for me to try. So, and I get excited when I talk about systems engineering. So if you do not understand something, please, by all means, talk to me, okay? And so, chart, please. Let me go over some of my background. Amy knows me in addition to my work in industry. I have half life there in academia. I have been working for many years, as long as I can remember teaching. And the last 9 years at the University of New Haven as an adjunct professor. And so my background, as I said, I came to this country in 1974, and I completed my master's in electrical engineering and a second master's in industrial engineering. There was no such thing then, systems engineering, although some of the courses in industrial engineering, there is an overlap between industrial engineering and systems engineering. So over the years, though, I understood my thinking evolved. Starting from electrical engineering and going through the work I did. My first really work was at Texas Instruments. They sponsored me to stay in this country. And it was totally different than what I did in college. It was about semiconductors. At that time, they were working with Kyocera, thin film, thick film components. Instead of having discrete components, they were doing this kind of research. So I got to see environmental testing, and I was going like, what did I do with 2 master's degrees to do this? Years later, really, very few people understood the connection, systems engineering, and going down to the component, not looking at the helicopter as a system, but understanding what are the issues due to environmental testing and other issues that they go trace down to the component level. So my advice is that no matter what comes to you, learn it, put it in your brain, and you never know, may come to be very useful later. So my work started fixed wing aircraft, F-16, years ago, and after 14 years with Lockheed Martin, my husband and I moved with UTC and working for Sikorsky. Helicopters are, the challenges are different than a fixed wing. It was a humbling experience for me, I have to say, because I was doing more advanced type of architectures and later ITT lead. But so I learned the challenges in helicopters. I did a little bit of functional work at the avionics and Comanche, and then I moved into, since 2004, I have been doing systems engineering. And I saw that looking the system as a whole instead of the pieces by themselves, this is where the value of systems engineering is. And I'm going to tell you up front, I'm not here to tell you that process is everything. It's not about the process. So I have become kind of opinionated that processes are necessary but not sufficient. So let's start the presentation. I want to leave some time at the end so that we can, I like to interact with the people, and if there are questions, we can have some open discussions, and hopefully I can answer some of your questions. So I don't know what's going on. Okay.
Is that working for you? I don't think it's going to work. I think you'll have.
Okay, thank you. All right, so my presentation has really, typically, you will see three parts. The first part is going very quickly over the traditional view of systems engineering and how we are implementing. And the focus will be in the implementation approach. Probably you have seen this. We look what we call the system of interest. For instance, for me working for helicopters, the system of interest is the helicopter. So we look at the helicopter as the overall system. And really, typically, we are not only looking at the mechanical or electrical components, but also we are looking at the logistics support. So when we say systems, it encompasses people, the arrangement of elements, including people, products, hardware and software, processes, policies and facilities, equipment and material, and all of these things are related, and through the integration of all these things, we get a system which that system has to provide and be sustainable throughout the product life cycle. Next, please. And so really the traditional view of systems engineering is an interdisciplinary approach, and encompasses the entire technical effort to get to a balanced system, a set of system solutions, and of course taking into consideration cost and schedule. So you have the performance, you have three elements: the performance, how the system is behaving, and if we meet the requirements, and then within the constraints, typically the cost and schedule are considered as the constraints. Although, if you can go back, although we say we integrate people, that integration is not totally at the stage where we want to go for truly sustainable people. So primary focus is computer-based systems. And yes, we have some human factor elements, very important piece of the equation. The operators and operational processes, operators we take always into consideration for the solution, but the operational processes sometimes do not get the attention that is required up front. So that's why I say may or may not be considered as part of the overall system. So this provides an overview. This is a generic product life cycle, starting with the technology development, then going to advanced, looking for some advanced solution. This is the advanced program. Then you do proposal, and then you go to what you have. Most of programs enter what we call engineering, manufacturing, and development. Before you go to production, you have some low-rate production. In other words, whatever you design, you go then and you don't build 100 helicopters. You build few of them to see if they will work before you go full-rate production. And here are the system engineering processes. You notice they're not in order of importance. Typically, there are two pieces of systems engineering processes, two categories: the technical categories and project management categories. Project management is like the technical project planning, management and control, and a lot of metrics, and under that category we have risk management. But risk management without the technical processes and planning without understanding the requirements really is not much of systems engineering. So we go back, and I may be biased, the technical piece, the technical effort, which consists of requirements development, requirements management, the decision, what type of solution, the optimization of the solution. These are the important pieces that you understand this first before you plan, right? So this is a generic, and so this chart shows the emphasis, and you can see risk management covers the full life cycle. You cannot get away from risk management. The same thing, the integrated project management. Requirements, the project integration, for instance, there are the dots that they are not all filled. We don't do much of project integration early on. We do, though, do some planning. So that chart to tell you where the emphasis of systems engineering is. Next. This is, looks a little bit complicated, but this is the DoD life cycle. This is the Department of Defense using this life cycle. And you can see that they start with technology development, the engineering, manufacturing, and development and production, deployment, and then operation support. And of course, most the emphasis of systems engineering is not just in the EMD. It is also to produce something that is it will be sustained throughout its life cycle. And so the major products we have prototypes, we have system performance specifications, and of course we are evolving, going to production readiness, looking at the technology readiness, low rate production, and of course at the end, part deployment and review. Now the major system baselines, this is the piece that all the OEMs, original contractors such as Sikorsky, that we build helicopters. This is where we get involved. We do get a contract, and we do what we call requirements analysis. And from the requirements analysis, we have reviews, systems requirements, and system functional reviews, where we look at the requirements and we define architectures. And from there, we go to preliminary design, and from preliminary design to critical design reviews. So at that time, systems engineers are involved in managing the technical baselines, and starting with the functional baseline, where we agree on requirements and we agree on architectures before we allocate requirements down to the supply chain. And when we say supply chain, it can be internal or external, because we have, we look at other IPTs, like for instance, avionics IPTs, that they do all the electrical. We flow down requirements to them so that they can start doing their design. And then in return, they decompose their requirements to hardware and software. And so this is how we manage the whole process. Okay, it looks complicated, but it is not. So really, what it takes, we start with the requirements. The customer comes in, and the customer has some needs and some expectations. And we have a lot of legacy programs. We don't all the time do brand new helicopters. And so the customer may come in and say, I want to improve capabilities. So the program I'm in for several years now, the compact rescue helicopter, is based on Black Hawk. Black Hawk is an older helicopter, but we put new systems to modernize and meet the compact rescue helicopter requirements. So we have the legacy considerations. Then we have a lot of regulations. You cannot go fly until the helicopter is certified to fly. And of course, it's a commercial helicopter. You have FAA. but military helicopters have their own framework. We work with new standards, it's a new standard. And different, the Army and the Navy and the Air Force sometimes have their own processes, but they're converging to one process. Very intense standard. We use the MIL standard, MIL handbook 516, that hopefully will become a uniform for the Army and the Air Force and the Navy. Then we have higher level specifications. These are specifications that the Joint Chief of Staffs are put in place based on strategic requirements that our government has. And then, of course, we have the constraints, cost, schedule, and technical variability, and the standards. Needless to say, I have been working 30 plus years, and I have seen these standards. I mean, it has become now a big industry out there to try to synchronize these standards, because everyone comes and does its own standard, and sometimes they compete. So there is a big opportunity there to do something with these standards. So there is a very good paper out. I met the lady White, UTC, had her TEACS requirements development course. She came from NASA. Her name is Ivy Hooks. I don't know if any longer has the consulting, but she wrote a book and a very good article. You can find it, it's available, that used to say why Johnny cannot write requirements. Of course, when she wrote it, there were not many Jennies in the field, and so now I said, please use this book, and read this article, but include Jenny, because it's not really characteristic only, to be fair, to men that they don't know how to write requirements. Women, we are equally guilty as well. So I did not want to be discriminating among male and female systems engineers, so I said, add Jenny there and go read the article. But it's a very good article, because what it says is we start at the wrong foot because we do not understand requirements. If we do not understand the requirements, and if we do not understand the technical piece, and this is where engineering comes into, it's not about systems engineering as process, abstract processes. It's about, as a double E, what you know about the requirement. If you're a mechanical engineering and you do not know how, or a propulsion engineer, and you don't know how the engine, what are the fundamental principles of an engine, the workings of an engine, how can you understand the requirement? So my point is that we have to understand the requirements very well. When I was starting as an engineer, we did not have any advanced tools, and therefore we had big rooms that we would put big specs, and we would sit around and talk about it. And I have to say that was very nice, because people would talk to each other. Probably sometimes we will be upset at each other, but eventually we would come to some understanding. Now we have tools, which, thank you, I love the tools. I would not want to go back to the age where we did not have tools, but we are missing something, and that something is the human interaction. And so we have reached to the point that we have wonderful tools. One of the tools that we use is DORS, which is a relational database, which is a good tool. It's been in use for a long time, but and we have brilliant young engineers that these things are trivial. Databases for people in your age and a little bit older, not in my age. These things are not very trivial. I know enough not to get into trouble. But what they do is they don't read the requirements, and they go in and they start linking the decomposition. So it's like garbage in, garbage out. So needless to say that it is not about the tools, it is not about the process, it is about understanding the SME, the subject matter expertise cannot be trivialized on the name of systems engineering. So next. All right, so what we do is, here are all some of the disciplines, and this, of course, it's a discipline how we do helicopters. We have the air vehicle, we have the air vehicle structures where we have analysts that they do structural analysis to make sure where we move the different components in the helicopter, it will be structurally, the integrity will be maintained. We have flight controls, we have thermal analysis, because you put a lot of avionics in a helicopter and you pack them very closely, there is not much of airflow. So even if the power dissipation and the heat is not very much, when you have a lot of them and the flow is not there, you're going to have thermal avionics cooling issues. And of course, we all know from basic reliability of systems, increased temperature deteriorates the performance, okay? So systems engineering puts the process in place and addresses both hardware, software, and then the SMEs get together. And you notice I have this like a marble, like a Greek marble, to indicate that it is the basis of systems engineering is the subject matter expertise. Otherwise, it becomes an abstract proposition. This pyramid right there shows that when we get the helicopter and we have systems requirements at the system level, all these things are being decomposed to different components, different subsystems. We develop what we call the system breakdown structure. And so everybody knows, for instance, all the flight control, hardware, software pieces, you know where they go in that pyramid. And really that is more like a map to tell us where we are and how we are allocating later the requirements. So the value added of systems engineering, we said it is obviously the process. Processes are necessary, but not sufficient. The sufficient piece is the SME knowledge and the integration. So now the integration is a very interesting proposition. I'm a little bit opinionated about this integration. You can learn in school about, you're a mechanical engineer, electrical engineer, you learn, you know this knowledge. But the integration piece to come into industry and start integrating and understanding how the double E's are interfacing with the mechanical engineers or the materials people or the chemical engineers or chemistry folks, that takes a little bit of experience. So, and I call it that systems engineering also, I can make the case that it is, as any engineering, is a little bit experiential. So if you don't have the project and see the full life cycle of the project, it becomes, you can take pieces, but you're not going to see the full aspects of integration. That's why I think it's very important to have projects, research projects, where people can go and see, students can see the full life cycle. Because unfortunately, when we have a program in industry, nobody is going to stop and say, I'm going to train the people and do something, training, and we have cost and schedule considerations. So it's very, you have to have people that are already trained into systems engineering. Next. Okay, so this is what I call traditional systems engineering implementation in a page. We start with the requirements. The requirements analysis, there are 3 loops. It looks very simplistic. But these 3 loops, the first is the requirements loop, the functional analysis, and then the design loop. These loops are not as simple as the picture shows, because you can go many times around these loops until you have an optimized solution. And so this is where the difference now between traditional systems engineering and model-based systems engineering will come. Because this type of going around the loop so many times, when you do not have modeling your system, it becomes very cumbersome. And so traditional systems engineering is very document-centric process, and we want to move from document-centric to model-centric type of approach. So systems engineering considerations, when we get So when you do the requirements analysis, we are establishing what we call the functional baseline. Although there is a little bit of distinction between functional and requirements. So we start with the requirements baseline, which is probably more like an agreement between us and the customer, I say us, the contractor and the customer, and then you get to the functional baseline where you define your architectures. And that is good. Up to that point, the tools that we have, such as doors, they're okay, although they're cumbersome because they're pretty much management tools instead of development tools. But where the breakdown happens is in the design, because once you get to the designers are going to start using other tools. They're going to start drawings. If it's an old system, they're going to use 2D drawings. Then they're going to go for more advanced in newer programs. We get a little bit of 3D modeling. So now you're between the traditional paper-driven drawings and then the models. And that's the transition to go from 2D to 3D is not always easy because you have legacy systems that you're not going to go and redesign, right? And so the dynamic object-oriented requirements is the doors where we put all the requirements. But over the years, I'm going now to the V model. Over the years, the emphasis has been not only to the requirements, but also the verification of requirements. And that can be very expensive. Fortunately or unfortunately, in order to verify something, you have to go fly, such as helicopter. You have to do, if it's not helicopter and it is like a ground, like the trainers, for instance, you have to do some type of a testing to verify and validate your requirements. So you will see later me discussing the difficulty, even if we go to model-based systems engineering, the difficulty you will have to have models that will be validated, and that's expensive. So think of it as writing software and you want to reuse that software, right? You have to be very careful to reuse the software. Sometimes it's easier to start from scratch, but there are advantages there to be gained reusing models, and we will talk about it a little bit, some pitfalls. And the spec, the system breakdown structure that I mentioned earlier, we have even a bigger architecture where we go and we say, okay, all the specifications and the test plans and test procedures, where are they? How do we distribute between the different teams? So this V diagram is not a process. It's to remind engineers that when you define a requirement, you have to define the verification method, because it's a lot of money. You can spend a lot of money for verification and still. So a requirement that is not verifiable is not a good requirement. So that's a way to say every time you do a requirement, you need to be looking at the verification. So these are the process pretty much and the tools. Next. All right, so the difficulty now starts because there are a lot of people involved. Like in the program, I mean, we are like 350 people. And so to communicate with all these people, just my group itself, we were around a little bit less than 100, and now we're like around 80. So to communicate and understand what everybody's work is, and then go and tell other people how we can exchange the information. This is where the whole difficulty of the application of systems engineering starts. So this one, this diagram shows how now we start engaging with suppliers, internal and external suppliers. We don't build everything at Sikorsky. We go out to suppliers and we give them requirements. So timely and accurate requirements flow down to our suppliers are very, very important. So you see, we do some things right here if I'm a contractor, and then I'm flowing down to my supplier some requirements, and then I'm changing my design because I'm trying to optimize. And guess what? Now I need to give new requirements to my supplier. My supplier already has done their design. It becomes kind of complicated. So where the tools come into play, to have good tools and models, it makes this exchange of information more efficient. But then the downfall is you have to have the same tools. Otherwise you get, I was in a project once where a supplier, I will not say the name, they said, hey, I don't use the same model version that you are using in my previous job, and I'm not going to invest money. So it was a big war, who's going to pay for, so that they can read the models that the supplier was giving us, and so that has to be an understanding from the beginning. And so systems engineering flows down requirements up to the PDR, the preliminary design review, and then once PDR is happening, we receive information. So you go down, you start from the high-level system, and you flow requirements down. But once the preliminary design happens, we need information from the small pieces, the suppliers or internal suppliers, to give requirements to make sure they will meet the higher level requirements. And that process can take a long time. Preliminary design review is an important review, and then we have what we call the critical design review. Most of the optimization starts with the preliminary design review, and then is being finalized at the critical design review. But often requirements may change, whether the customer changes their mind, or whether we are finding out that, well, we thought we were going to meet the requirement with such capability, but it's not, we need to make change. So then the longer you wait to discover things like this, the harder it is to go back and start the whole systems engineering process again. So you can tell that, as we said, timely and accurate requirements. I have these stars because these charts I use because I do in-house training, and also program managers. I teach them, and I tell them you cannot have suppliers under contract after the CDR, after the Sikorsky's higher level CDR, because that's a big risk, and so it's just like what we call a cheat sheet, for managers to summarize what needs to be done. Next. All right. I'm entering what we call the program or project, technical project management. The technical project management encompasses the project scope, the acquisition strategy, and program operating plan. And this is at the program level. It's not the technical. It's like at the high level. There is a program manager in every project we get. And then we have what we call the integrated master plan. The integrated master plan is broken in milestones, and each milestone has entry-exit criteria. And we have to meet these criteria, otherwise the customer will not be satisfied. These are contractual things. The integrated master plan feeds the system engineering management plan, which is an overarching technical plan. My job as a chief system engineer is to make sure the process and the technical effort is executed according to the systems engineering management plan. So the systems engineering management plan is a plan, it's like the playbook, so to speak. Everything that happens in the project technically has to be aligned with that plan. So it points to many different plans, the software development plan, and it's one, the hardware plans, and so on. It has three parts, the planning and control, the processes, and the specialty integration. where really the value added of the implementation is there. So you see, the systems engineering process is only one piece of the equation. There are two other pieces, which is the technical program implementation and control through the IMP and the IMS. See the integrated master schedule as detailed master plan. So you start with the plan, the integrated master plan, and then you go down. Programs can have like thousands of lines. I mean, you can make it like typical proposal can have 8,000 lines of schedule, and then once you get out the contract, it explodes. So we have tools. We used to have, when I started, Microsoft project, MS project, and then now we evolved. We have tools that do wonderful planning. Primavera and other tools are available, where the risk also is embedded in these tools to do risk analysis, because the risk will take into consideration cost and schedule, and so it's nice to have it where your schedule resides. So the project-defined processes, this is how I started the whole thing. I manage processes, and what we do, the process, we allow tailoring, and you have to be flexible, because the process should not be dictating and overtake contractual requirements. But any tailoring has to be controlled, meaning has to be approved. There are some things that we cannot tailor out. Otherwise, we will not be compliant with different frameworks that we need to meet internally. In CMMI, the capability, maturity models, these are things that we still use. Next. All right. So, which brings me to, we do have decision-making tools when we do design considerations, but these tools are not integrated with the other tools. For instance, we have doors here. We have decision-making tools that they start from Excel to more advanced analytical hierarchical process. And so what happens is we are missing the point, because we are trying to figure out how to use these tools and when to use it and how to use it. And the point is that when you are early on in a project, the cone of uncertainty is a lot bigger. And so this is when you need to use the decision-making process and tools. Unfortunately, we run to a solution. It's a sub-optimized solution often. We look at probably cost. We may not look at the schedule, and we may not look at the performance. And then as we go further and get to the operational and support, it's very, very expensive to go back or to find out you made the wrong design decision. So I tell my people and the program managers when I teach risk and other courses, don't be afraid of risk. Don't be afraid to do decisions, make decisions even that are cumbersome and may not be, use the word for a lack of a better word, politically correct, but you have to address the problem. Because now, knowing the issues, you have a lot more chances to optimize your solution than wait later and say, oops, I forgot something. So this is what it is. So from spreadsheets to more advanced tools, we need to be going, but they're separate. They're not integrated. Next. Okay, and of course we have the famous risk cube. We use, this is qualitative risk management, and the quantitative risk management is a lot more structured, and it uses a lot more advanced probability theory. And I can tell you we do not. We do not, because it's very few people understand probability, very few people understand what correlation factors are, very few people can overcome the cultural biases associated with risk. So guess what? We are reverting on qualitative assessment. And what this qualitative assessment is, you have the probability on this axis, the y-axis, and you have the consequences at the x-axis, and then you have a group of people that come in and say, so what do you think the risk will be? So someone may say, if someone has a lot of experience, they tend to be a little bit more conservative about it, and they will say, well, I think we have 60% probability that this thing will happen, or we will not meet this requirement. And if we don't meet this requirement, the consequences, it's going to be a disaster. They get the extremes. So immediately they will put you on red. Well, typically management, they don't want to hear about problems. They want to hear about solutions, and rightfully so, right? They pay us, they pay engineers to find solutions, not to tell them that there is a problem. So over the time, there is some tendency, and that's a cultural thing, instead of seeing the red as like a stop light. You see red, what does it tell you? Do not cross, right? It's a warning. That does not mean if the red light turns and you go jaywalking, you're going to be killed, right? So, but unfortunately, it's a cultural thing. Probably the colors, probably we need to change the colors and not talk about colors, talk about levels. But when people see red, they get a little bit jittery. And then you have also the other side, people who don't have enough experience and they're, perpetually optimistic. So they go, oh, no problem, it will happen, because they don't see the details, right? And so you have this mixture of people. So a good thing is when you do risk analysis or risk assessment, to have a mixture of people. And of course, then you have the people, engineers tend to be shy. Not all engineers, don't look at, I'm not shy, I'm very opinionated. So you have the people who are opinionated and they get up and they make the statement and say this is wrong. And then there are people who are very quiet and then you get a little bit extremes. So there are a lot of built-in biases when we do risk. So that's why you need to get into from quantitative to qualitative state. And the tools that are embedded in schedule tools, they can do this analysis. And they assume different probability density functions. And from there, you can do some correlation and you can get your S-gaps and so on. All right. So. All right.
Too still.
So I want to talk a little bit about effectiveness of the traditional systems engineering. And I can tell you there are two obstacles into the effectiveness, actually a little bit more than two. I'll talk about the big obstacles. They're very document-centric. And document-centric, you can drown in documents, but DoD is still using the document-centric framework with the contractual deliverables. And so we have to follow and meet our obligations. So you see, all these tools, like we have key performance parameters, we have the system considerations, we have some goals and criteria with our decisions, decision-making tools, we have the risk. We have one thing that we pay attention several years now is technology readiness maturation and manufacturing readiness levels. And these two need to be aligned. We have had problems where someone wants to have some nice idea, but the technology was not there and it was not conducive to the constraints that the customer would give us. So the customer has a risk. They say, hey, that's not a research program. This is a program that has so much budget and so much schedule. So technology readiness level and the assessment is in all programs now, at least for DoD, because we see it as a risk reduction and the customer sees as a risk reduction. But it used to be, you used to have the technology readiness, and then, by the way, the manufacturing readiness was somewhere there. And now there is an effort for some years to integrate, and UTC was very big in that kind of integration between the design and the manufacturing. Because the people who are in operations and manufacturing, they have different objectives, and the designers and the system engineers drop the things without taking into consideration what the manufacturing people are expecting, that's a problem. So what this chart shows is we have systems, but they're not connected. Okay? So connectivity, and then on top of this, we have a lot of standards. Don't take this as the latest, because I'm sure they have been evolved, but I had this chart ready. I did not want to make another chart. There is a big initiative of overhauling the different standards, and at one point I was involved also making common standards between the US and other countries, like Europeans do a lot of work in systems engineering, but they use different standards. So it would be nice for everybody to get together, but there's a lot of money to be made in standard synchronization. So I'm not sure who wants to give up first. So, but there is a good initiative, and I think the more tools we use and moving to model-based systems engineering, we are going to be forced to find standards that are conducive to these tools. And so I wanted to let you know that there are so many of them, and the standards really are not going to solve the problems that we are seeing, but they exacerbate the problem. Because the younger engineers don't have the experience to go back and say, oh, okay, I have CMMI some time ago, I had CMM. They don't have that knowledge, so they look at something new, while for those of us that are in the trenches for 30 years plus, you recognize it and say, oh, okay, it's another variation of what we did some years ago. Okay, next. All right, there was a study some time ago. I was involved in that group. Very difficult to get actual data so that to have the validity of the study. The study was led by Carnegie Mellon and was sponsored by the Department of Defense to talk about the effectiveness, because everybody gets into process improvements and they think this is another silver bullet that resolves the problems that we are facing. But there is no such a thing, silver bullet. So they did some industry-wide survey to see the effectiveness. Well, how did they manage to define effectiveness? It's based on cost and schedule. It's very hard, though, to go and get to the company and say, Sikorsky or Lockheed, give me your data. How much did you spend for this? Where did you stay within the allocated budget and schedule? They're not going to give you this data. So look at this research that was done with a little bit of as indicators. So what they did, they said that from the analysis that Carnegie Mellon did, and the research is available, I also did some, I'll get into this. So the projects with better systems engineering capabilities deliver projects that are better, because people have some process to follow, and that perhaps this is where the research focused. So
how much better? How much better is that?
Well, that is the question. How much better? It was in different buckets, the red and the yellow, to show indicators using the alpha coefficients to say, well, a little bit better. And so they came up with a class of projects that clearly they had higher level of CMMI. CMMI goes up to level 5. And big companies, they claim, that there are 5, and there is a prescriptive type of processes that you need to follow. So over the years, I found out...
is for software, right?
Excuse me? CMM was for software, and you're correct. We could not be under contract years ago without being certified that you're CMM. But then became CMMI because people said, okay, you're focusing on the software, which is after the system's requirements have been defined. It's a little bit too late. So we moved to the CMMI, which is integration, maturity model. So I wrote a paper and that was part of, I was trying to reinvigorate my PhD work, which I found myself started thinking too much. about it. It's not about the process. And I know some people may not like me saying this, but we spend a lot of money about improving processes, and we do not see the payoff in many projects. So I started doing a little bit of research, and my focus was on the human elements of the equation. And I went like, okay, and so I studied 3 seminal about work definition. And I just found out, my data showed that it is not just a process, it's about process implementation. And the people who implement the process, we do not pay attention to that piece. In other words, we do not train these people on time, and the learning curve is not there. So guess what? We end up at a deficit when we start the project, okay? So this is, while the importance of practice of systems engineering is widely recognized, its effectiveness remains an elusive goal. This is where was my opening of my paper, and I presented it at the American Helicopter Society, and everybody wanted for me to get actual data. Of course, the company, you will have hard time it's very hard to get this data and show, which projects, what levels of competency, what engineers work. It's very, very hard. And so it remained, they wanted me to continue. The engineers wanted me to continue because they said, oh yeah, when a company gives us only 10 hours of training every year, and I don't have enough time to devote to my program and also get the training to the new tool, so it remains, the effectiveness becomes an elusive goal. So the tradition, yes?
Why is it difficult for you to get data?
Well, this is, I need to contain myself since I'm being taped there. I believe it is because we have moved too much in litigation type of society. You see, it's easier to blame a process than to allocate at least some partial blame to the implementation. And the implementation involves people. So now the people, I don't blame the people, I think people need to be trained, right? The schooling that we all receive is not enough because engineering is an experiential profession. Therefore, I can see also the corporation's point of view that when a program comes in and we have obligations to meet our cost and schedule and performance, it's very hard to stop and say, I'm going to train a few people. So there has to be some way that we have a pipeline of trained engineers to take on to the next program that will come along. And this is what I believe, where the breakdown. And I am biased, and probably because I'm older now, I think the technical effort has been marginalized over the years because we have the constraints that are very difficult constraints, cost and schedule constraints. Therefore, the technical effort is still there and it is being considered, but if it does not meet cost and schedule, it's not going to. So it's a very complex, it's not one answer, but I'm a little bit opinionated and biased in my view. Why? So
isn't it the corporate mindset that standard work? I know that what we call
that's the thing.
Work replaces humans and
but standard work can make people dumb. I mean, I don't. Someone needs to turn off the. I hope it will clean that tape before. So I guess what I'm saying. Standard work, and why I say this, I remember when I was doing my second master's, and I got to the course for time motion studies, and oh my gosh, Satish Kamath was a dean, and also was the professor who was teaching. And I was just like all over. What is this? This is oppression. What do you mean? You're measuring someone, how you will do this, and you're going to do this, and then you're going to do this. And he was looking at me like, who is this revolutionary in my class? Because I felt then that it was just not a good way to motivate people to do work, okay? To do something stupid over and over and over again does not motivate people, right? So we've got to make the conditions so that people don't feel that they're doing something either that it's not important, or you do something, you spend your time, and then someone says, thank you very much, but it's not going to meet cost and schedule. That's demoralizing, isn't it? So there are a lot of complexities that, and then I thought, okay, because I worked in commercial, and there I was complaining too that they don't pay attention to things because it's like disposable. It was time products, and I was going like, nobody cares about if the design is reliable and so on, because in this country it's very inexpensive to go get a new calculator. And so defense is the same. And then I started saying, oh, well, probably if you're in biology, my son was doing his PhD, probably when you're in biology, you cannot mess around with people's lives, Well, we know what's happening in the industry. Look, this is how it is. Cost and schedule, we cannot get away. My problem is it has to be balanced. You have cost, schedule, and the performance. And there is a fourth dimension that nobody talks about, the people, the human element. And if we don't consider that human element, so you will see my next part is not about technical systems, but socio-technical systems. And this is where my heart has been for some time now, but nobody wants to hear about socio-technical systems where I work, just my view of things, because I have cost and schedule, and I can tell you, if one of my engineers comes and talks to me about the things, I talk, I'm like, okay, let's have happy hour talk. Now I want you to go and do what I want you to do, to move the schedule and to move that's the reality of the thing. Because if we do not meet cost and schedule, we are not going to have business. If we are not going to have business, we are not going to have employment, and we are not going to learn. And so for me, I have been lucky to work in projects and see the full life cycle, and I see the other side of the corporation, so it has to be a balanced approach. All right, so this is something, some things that I give, it's just common sense, the traditional systems engineering process, it's more of a common sense and some steps. For instance, all the requirements are analyzed, ensure accurate and timely flow, provide a systematic way of planning and managing, provide and proactively managing risks, and establish the foundation of all aspects, optimize the system, and then the payoff is at the end. Next. So now we're going to get into the latest, and it's not new, model-based systems engineering. It is not new. I can tell you 1981, I had my first baby, my daughter, and my husband was doing research with Mantec, and I was bored out of my mind because I stayed home with the kid. And he was bringing all these things from Mantec, and I was reading about IDEF 0, IDEF 1, and things like that. And they were trying to model the whole factory at LTV, right? And it was just fascinating to see the work that they were doing to model the whole factory operation using model-based systems engineering. These things are not new. So then why these things have not been widely used today? And we will talk about it. It's a little bit of both. So this is a chart from CORE. The first, and why I like CORE, because it is based on IDEF type of architectures, IDEF 0, IDEF 1, and things like that. And it is very conducive to all engineers, except those of you who are writing software. you want Rhapsody, you want, to get down to the weeds. I like to see block diagrams, probably because I was in control systems in electrical engineering, and I understand the block diagram, input, output, and when it goes down to very detailed type of software, I want to see first the top level architecture. And so what happens is the benefits of using realized through integrated process, enabling an efficient development and management of the functional, allocated and product baselines, shortcomings due to separate design tools. And I'll tell you what is happening. It doesn't matter whether it is core or any other system. The requirements can be handled with most all of these systems. Where the breakdown happens is when you start getting into the third loop that we talked about, the design loop. The design happens using other tools. Well, these tools are not integrated in core and anything like that. You have to go use CATIA, you have to use LCA, you have to use different tools. So, you still have core or any other system that handles very well your functional baseline requirements and functional architectures. But when it comes to the actual physical design, where you have to do the drawings, they're separate tools. These tools are not integrated. And so it's a misconception also to say, yeah, you eliminate some paperwork, but you still have paper for the drawings. Because guess what? There are going to be people who do not understand CATIA, and they want to touch a paper. And you're going to have to give a paper. And plus our DoD still works with these standards where we need to give them paper also. So you can spit some papers, documents out of these tools, but still it's not totally there. Efficiency is realized because all of these things being connected, the models are connected. Therefore, if you change one model immediately, all the interfaces are being updated. While when we had doors before, we used to take Visio and put block diagrams to doors, right? Then if we were making changes of requirement, we update the Visio, import back to doors. There is that kind of inefficiency. Well, tools like that, the architectures and the interfaces of these architectures are being updated, and this is the efficiency.
So Theo, we're a little short on time, so
Okay.
let's see if you can summarize and
Yes.
maybe take a few questions and wrap.
Yeah. So let's move on. So the efficiency, I just talked about it. Challenges is the developing the library of models, the complexity, integration, validation, tuning of the models, the tailoring of the models, and of course developing the SME skills. Not everybody can do modeling. Okay? Let's be real. Not all engineers take courses in school to learn to do modeling. Plus, the models need to be validated, otherwise will not be valid. And then the funding. Who's going to fund it? Next. And so when we do all these things, you still have, the point I'm trying to make, and I finished, it's not just the processes and the models. We need to focus also, shift our focus from purely technical systems to socio-technical systems. And in that case, a socio-technical system, you have to deal with the organizational complexity. And if someone tries to model the organizational complexity, probably will be Nobel Prize winner because, to model human beings is kind of complex. We are all different, right? And thank you. That's good. Diversity is good. Validation of models varies. Diverse non-integrated tools. Inefficient requirements flow down. Prime focus on system and functional architectures. Predominantly 2D drawings, old and often conflicting standards. Next. Okay, so my approach and what I propose is to look at a new model beyond model-based systems engineering. What I call is the enterprise model. I'm defining effectiveness. This comes from an abstract that I never put the paper out there because I have been busy with my work, and I'm trying to develop that model that's people, process, product, and performance. And if you look at the effectiveness as an integration over the product life cycle, You have the process, you have the people, and the people where we have been talking that it has to be a collaboration between the government, academia, and industry to build these models. But guess what? The silos and who's going to put, but if the government puts the money for the models, so everybody can use, guess what? Someone is going to be smart enough to say, my model, there's a big war out there for patents, and this is how the economy is growing too, right? So performance, product, process, and people, that is my proposed effectiveness. And next. Go ahead. Okay, so what I have been proposing is to start with the traditional systems engineering, go to model-based systems engineering, then get the model-based systems engineering and add the 2D drawings, and then go to 3D, and that has to be incremental. You cannot wake up in industry where we are, for instance, and say, okay, I'm going to go to model-based systems engineering and abandon anything else, or I'm going to go to 3D model. It has to be incremental because we have legacy systems that we need to leverage, okay? And then at the end, right here, oops, I'm leaving this. I'm proposing a decision hub where you have all your risk and your decision-making tools, where you do your optimization. And then the last piece is it feeds metrics. Metrics, right now, in my opinion, are so inefficient. They're not leading indicators. Sometimes can give you the wrong information. So if we do not do this kind of approach, in my view, we will not be able to reach the effectiveness that we all want to do. So this is something to ponder. We may say, take me to the moon, want to play with the stars. The song, Take Me to the Moon, came to mind when I was doing this, and people say, where do you want to go? Well, you cannot go to the moon. You need to take some incremental steps. Sorry, I had to get through quickly on these things, but decision-making tools, optimization tools, having a program that is solely based on the technical, the SME, whatever it is, the engineering discipline, whether it is mechanical or electrical or computer science, you need a collaborative type of involvement to get an optimized system. So thank you for your attention, and I'll get questions.
So let's take one or two quick questions in the interest of time.
Yeah.
You've already had a really good discussion, which is fantastic, but let's continue that a bit. If anyone has any leftover questions. Yeah.
So someone gives you requirements for a control system. For a system, you define requirements for the controls of the system. You give it to the controls engineers. That controls engineers tells you that realizes that there's no way, because of the system dynamics, to accomplish that control requirements. And they come back. There's about a year time difference between the one analysis and the other analysis. How do you level these two things together? Because you show the loop, but the loop on paper doesn't really show that it takes 6 months before you actually know that you need to go back, and you cannot necessarily go back. Is there
Fortunately for the programs we do have established transfer functions and models. For a helicopter.
At the point that you're still analyzing
we still analyze requirements, and we have people that even during the proposal, they look at the performance to optimize, range, payload, and other parameters, key parameters that the customer will give. And so, but still, when you start looking, so you may optimize the control system. You may come and say, okay, I'm going to use, such and such control law. But when you take that control system and you integrate with all the other pieces, this is where the difficulty comes. to balance. And the idea is not to find these things late in the program, because if you find these things late in the program, it's going to be very difficult to go and redesign. And plus, when we do what we call the systems requirements review, it's like we sign and say we will meet these requirements because we have done some upfront analysis. But if you go lower to lower detailed design, you will find issues. And then either you have to get with a customer and say, look, we need to do trade studies to find some equivalent solution, or you're going to ease the requirements. And this is where the tug of, give and take starts. But that's why I said that we have to have tools to be able to do this quick analysis upfront when your trade space is a lot bigger, a lot larger, so you can make decisions. Because as you go further, the cone of uncertainty is reduced, but also your opportunities to make changes is being reduced.
Right, you should spend a lot of time on the concept stage.
Yeah.
So the problem is they quickly make decisions. And
Yeah.
That's what causes this 25-year problem.
Exactly. Thank you for the point. What happened is, like, it used to be we had like 6 months and even more to do proposals. Now proposals it's like 3 months, and it's very hard to do some detailed analysis. And so you start and you say, yeah, I think it's good enough. I'm going to make it. And the thinking is that, look, if we find problems, we're going to spend some money to fix it instead of doing it from the beginning. And some problems you can fix, if you spend a little bit more money, but there are some problems that are inherently in the DNA of the legacy design that you cannot fix.
Thank you so much for your insight.
You. Thank you very much.
This was a really, really great talk.
Thank you.
Let's thank the speaker one more time.